Welcome to Softly Curious. Tonight, we begin somewhere almost invisible. Not on the ground where snow gathers, not in forests or cities softened by winter light, but high above them, inside a cloud where shape begins before it can be seen. Every snowflake starts as water. Not a drop, not yet ice, but a molecule made of two hydrogen atoms bonded to one oxygen atom. The bond angle between those hydrogen atoms is not straight. It sits at approximately 104.5 degrees. That small angle, quiet and fixed, gives the molecule a subtle asymmetry. One side carries a slightly negative charge, the other slightly positive. Water is not neutral in shape, even when it appears calm. When temperatures fall below freezing, those molecules slow. They begin to arrange themselves according to electrical attraction. The slightly positive hydrogen of one molecule aligns toward the slightly negative oxygen of another. This alignment forms what are called hydrogen bonds, weak individually, but powerful in number. Hydrogen bonding means attraction between partial charges, not full ionic bonds, yet it is strong enough to organize billions of molecules into repeating patterns. That hexagonal lattice is not decorative. It is structural. The six-sided symmetry that later defines a snowflake is already present at the molecular level. Long before branches form, long before a shape appears unique, the rule of six is quietly established. But structure alone does not create a snowflake. A crystal requires a beginning point. In the atmosphere, that beginning rarely happens spontaneously. It usually needs a surface. This first step is called nucleation, the initial formation of a stable cluster of molecules. In most natural clouds, this is heterogeneous nucleation, meaning it happens on something else. The atmosphere is never empty. Tiny particles drift constantly through it, dust lifted from deserts, sea salt carried inland by wind, pollen released from forests, microscopic ash from volcanic eruptions that may have occurred thousands of kilometers away. Each of these particles can act as a nucleus, a microscopic platform where water vapor can begin to freeze. Volcanic ash is particularly effective. Its irregular surface provides countless microscopic crevices where water molecules can settle and organize. Sea salt particles, formed when ocean spray evaporates, also provide stable surfaces for ice formation. Even high above the ocean, salt crystals rise and travel in air currents, becoming silent participants in snowfall, far from their origin. At high altitudes, especially in cirrus clouds, temperatures can drop well below -20 degrees Celsius. Cirrus clouds are thin, wispy formations composed largely of ice crystals rather than liquid droplets. In these regions, the air is cold and dry, and ice forms directly from vapor without passing through a liquid phase. This process is known as deposition. Water vapor becomes solid ice without becoming liquid first. For deposition to occur, the air must be supersaturated. Supersaturation means that the air contains more water vapor than it would normally hold at equilibrium with ice. It is a state of imbalance. The vapor pressure exceeds the saturation point, creating conditions where water molecules are more likely to attach to a surface than to escape from it. Supersaturation is not dramatic. It is simply a slight excess, a quiet abundance that allows growth to begin. Inside a cloud, temperature is not uniform. Even within a small volume, tiny gradients exist. A fraction of a degree can influence how quickly molecules attach to a growing crystal. One region of a cloud may encourage flat growth along a plane. Another may promote vertical extension. These microtemperature differences guide early formation long before the crystal becomes visible. In most cases, freezing begins around particles at temperatures between -5 and -20 degrees Celsius. However, if the air becomes cold enough, around -40 degrees Celsius, water droplets can freeze without any particle at all. This is called homogeneous freezing. At that temperature, Molecular motion slows so dramatically that water can spontaneously organize into ice without external support. But such extreme cold is required. Above that threshold, the atmosphere almost always relies on heterogeneous nucleation. The distinction matters. It explains why snow formation depends not only on temperature, but on the invisible inventory of particles suspended in the air. A cloud rich in aerosols may produce ice more readily than one that is relatively clean. Pollution, volcanic events, and ocean spray subtly influence snowfall patterns by providing or limiting nucleation sites. In the early 20th century, scientists began to investigate these processes systematically. Irving Langmuir studied surface chemistry and phase transitions, helping to clarify how molecules behave at boundaries between gas and solid. His work contributed to understanding how condensation and freezing begin on microscopic surfaces. Later, Yukichiro Nakaya at Hokkaido University became the first scientist to successfully create artificial snow crystals in laboratory conditions. By controlling temperature and humidity, he was able to grow ice crystals on thin fibers, observing how subtle atmospheric variations produce distinct shapes. His work demonstrated that snowflake structure is not random decoration. It is the direct physical expression of environmental conditions. Inside a cloud, once nucleation begins, a tiny hexagonal prism forms. At this stage, the crystal may be only a few micrometers wide. It is invisible to the human eye. Yet even at this scale, its symmetry is already defined. 6 faces, 6 corners, each determined by molecular alignment. Water molecules continue to collide with the growing crystal. Some bounce away, others adhere. When the surrounding air remains supersaturated with respect to ice, attachment outpaces evaporation. Growth becomes steady. But growth is never perfectly even. The corners of a hexagonal crystal protrude slightly into the surrounding vapor, making them more accessible to incoming molecules. Because of this, corners often grow faster than flat edges. Even in the earliest stage, geometry begins to amplify itself. Small differences become structural tendencies. High in cirrus clouds, where temperatures can reach -40 degrees or colder, homogeneous freezing may suddenly create numerous tiny ice crystals at once. In slightly warmer cloud layers, freezing is slower and more dependent on particles. These differences influence how many crystals form and how they compete for available vapor. A cloud is not a uniform field of identical beginnings. It is a shifting environment of micro-conditions. Each nascent crystal exists within a slightly different temperature, humidity, and airflow profile. Even before branching begins, individuality is seeded by circumstance. The molecular angle of 104.5 degrees, the hydrogen bonds, the hexagonal lattice of ice, i.e., the presence of dust or salt or ash, the quiet excess of supersaturation, the subtle temperature variations inside a cloud, and the threshold near -40 degrees, where spontaneous freezing becomes possible. All of these factors converge before a snowflake ever resembles what we imagine. Nothing dramatic announces the beginning. There is no sudden pattern, only alignment, only attachment, only a gradual commitment to structure in cold air. Long before it drifts downward, long before it reflects light in a winter sky, a snowflake is already geometry in progress. Once a crystal has formed, its life is no longer defined only by molecular structure, but by movement through air. Growth does not happen because molecules decide to attach. It happens because water vapor diffuses through the surrounding atmosphere, drifting from regions of higher concentration toward the colder, solid surface of the crystal. Diffusion simply means the gradual spreading of molecules from crowded areas to less crowded ones. In a cloud, this invisible migration becomes the engine of expansion. As vapor molecules settle onto the ice surface, they do not attach evenly. Some areas of the crystal are more energetically favorable than others. Flat surfaces may grow slowly, while edges and corners capture molecules more efficiently. This uneven attachment leads to what physicists call faceting, the development of smooth, flat faces along preferred crystallographic directions. A facet is not decoration. It is the surface revealing the underlying order of the lattice. But stability does not last forever. When supersaturation increases, growth can become unstable. Tiny protrusions on a surface extend slightly farther into vapor-rich air. Because they are more exposed, they gather molecules faster. This process is known as branching instability, a feedback loop in which small irregularities amplify themselves. A subtle bump becomes a ridge. A ridge becomes an arm. Temperature and humidity together guide this transformation. There is a narrow atmospheric range in which flat, plate-like crystals dominate, and another where elongated columns become more likely. Between roughly -2 degrees Celsius and -15 degrees Celsius, subtle shifts in temperature can redirect growth entirely. Around -2 degrees Celsius, thin plates often emerge. Near -5 degrees Celsius, needle-like forms begin to appear. Closer to -15 degrees Celsius, elaborate dendritic structures, the classic star-shaped snowflakes, become more common. A few degrees can redirect geometry. In polar regions, where air is consistently cold and often relatively dry, slender needle crystals are frequently observed. These elongated forms grow when vertical extension is energetically favored over lateral spreading. They may look simple, almost austere, but their simplicity reflects strict atmospheric discipline. The environment leaves little room for ornament. At slightly warmer yet still sub-freezing temperatures, hollow columns can develop. A hollow column forms when growth along the edges outpaces growth at the center of a prism face. The interior lags behind, creating a channel that runs through the crystal. The hollow does not represent decay. It is a record of uneven deposition rates across the surface. The transition between plate and column forms is not abrupt. It is gradual and responsive. A crystal may begin as a column in one temperature layer, then drift into another region of the cloud where lateral growth becomes more favorable. As it passes through changing humidity, its structure adjusts. Growth directions shift and new layers overlay older ones. The shape becomes a timeline of atmospheric travel. In mountainous regions such as the Alps, dendritic crystals often appear during moist, moderately cold conditions. Dendrites are branching forms resembling fern leaves, though the similarity is structural rather than biological. Their arms subdivide repeatedly because branching instability accelerates at higher supersaturation. The air supplies vapor quickly, and protruding tips harvest it most efficiently. Each branch competes quietly with its neighbors. This competition is influenced by airflow. As a crystal falls, air moves around it. This movement enhances vapor delivery to certain surfaces, a phenomenon known as the ventilation effect. Ventilation effect means that airflow increases the rate at which molecules reach the crystal, effectively speeding growth. A gently rotating snowflake may experience uneven airflow, encouraging asymmetrical expansion along certain arms. Inside storm systems, especially vigorous winter fronts, turbulence intensifies these processes. Strong upward currents can suspend crystals longer within supersaturated layers. The longer they remain in growth-friendly regions, the larger and more intricate they become. Growth accelerates not because the crystal changes, but because the environment sustains it. The laboratory studies at California Institute of Technology have explored these mechanisms in controlled conditions. Kenneth Liebrecht has demonstrated how carefully adjusting temperature and vapor pressure can reproduce the diverse forms observed in natural snowfall. His work confirms that snowflake morphology is not random artistry. It is the predictable outcome of physical laws operating under shifting parameters. Morphological instability, the tendency for small structural differences to amplify under certain conditions, ensures that no crystal remains perfectly simple for long. Even a nearly symmetrical plate may begin to branch if supersaturation rises. Even a clean column may develop surface roughness when growth becomes rapid. Instability is not disorder. It is sensitivity. By the time a snowflake leaves the cloud layer where it formed, its shape is a composite record of diffusion, temperature shifts, humidity gradients, airflow, and time. Each arm, each hollow, each delicate branch reflects a specific atmospheric moment. The crystal does not design itself. It responds. In this way, the atmosphere becomes both sculptor and script. Growth by diffusion provides the material. Temperature selects direction. Humidity determines pace. Airflow modifies exposure. Instability amplifies detail. Together, these forces transform a microscopic prism into a visible structure, shaped not by intention, but by condition. If a snowflake appears delicate, it is only because we are looking at the surface. Beneath that surface lies an insistence, a quiet rule that cannot be negotiated. 6 arms do not emerge from artistic preference. They emerge from structure. The hexagonal symmetry of a snowflake is not added later. It is required by the internal arrangement of its molecules. When water freezes into its most common crystalline form, the molecules settle into a repeating lattice. A lattice is simply a regularly spaced three-dimensional grid, an ordered pattern that repeats in space. In ice, that grid arranges itself in a way that produces six-fold symmetry when viewed from above. This is not unique to snow. Many crystalline materials obey strict internal geometries. The field that studies these repeating structures is called lattice theory, the mathematical description of how points can fill space in orderly patterns. In this framework, a crystal is not a solid object first. It is a spatial repetition. Each point in the lattice can be translated, meaning shifted by a certain distance in a specific direction, and the structure remains identical. This property is called translational symmetry. Translational symmetry means that if you move through the crystal by exact repeating intervals, the environment around you looks the same. The pattern does not change. It extends. In hexagonal ice, this repetition organizes around 3 primary axes lying in a plane, each separated by 60 degrees. A 4th axis extends vertically. These directions are known as crystallographic axes, the preferred orientations along which growth and bonding occur. They are not visible lines. They are directions of structural permission. Growth along these axes is not uniform. Ice does not expand equally in every direction. This uneven expansion is known as anisotropic growth. Anisotropic growth means that a material grows at different rates depending on direction. In snow crystals, certain crystallographic faces accumulate molecules faster than others. As a result, the shape elongates or spreads depending on which axis dominates under given conditions. The necessity of internal symmetry was already a subject of curiosity in the early 17th century. Johannes Kepler, in his small treatise Strensiu Dinae Sexangula, wondered why snowflakes consistently display six-fold geometry. Without access to molecular theory, he proposed that close packing of spheres might explain the repetition. He could not see the lattice, yet he sensed that geometry must originate from structure. Centuries later, Auguste Brevet formalized lattice theory by classifying all possible three-dimensional lattice types. His work demonstrated that crystalline materials can be described as mathematical point grids extending through space. Ice belongs to the hexagonal crystal system in this classification. The snowflake's 6 arms are not accidental outcomes. They are consequences of belonging to that system. The same structural logic appears in other materials. Quartz crystals also display hexagonal symmetry, though their chemistry is entirely different. Quartz is composed of silicon and oxygen arranged in a repeating framework. Yet when quartz forms well-defined crystals, it often reveals 6-sided prisms. The repetition arises from internal order, not from similarity in substance. Geometry in nature does not depend on aesthetic resemblance. It depends on atomic arrangement. Basalt columns provide another example. When lava cools and contracts, it can fracture into polygonal columns. These columns are frequently hexagonal, forming structures like the Giant's Causeway in Northern Ireland. The similarity to snowflake geometry is not molecular, but structural. When forces distribute evenly across a surface, hexagons often emerge as efficient solutions. Not all carbon crystals behave the same way. Graphite and diamond, both composed of carbon, demonstrate how different lattice arrangements create different properties. In graphite, carbon atoms form layered hexagonal sheets that slide over one another, making it soft and useful for writing. In diamond, carbon atoms bond in a rigid three-dimensional network, producing extreme hardness. The difference lies in lattice structure, not elemental composition. Snowflakes follow their own structural commitments. The 60-degree repetition is embedded in their crystallographic axis. When a tiny prism begins to extend, each arm grows outward along one of these allowed directions. Even if external conditions vary slightly, the fundamental angles remain fixed. The lattice does not negotiate. Translational symmetry ensures that the microscopic environment at one point in the crystal mirrors that at another, provided you move along exact repeating distances. This uniformity at the atomic scale gives rise to macroscopic symmetry. When millions of molecules align in repeating order, the repetition becomes visible. Anisotropy adds variation within constraint. Under certain temperatures and humidity levels, growth along the basal plane, the flat hexagonal face, may dominate. Under others, growth along the vertical axis may accelerate. The internal grid remains the same, but its expression shifts depending on environmental encouragement. A snowflake therefore embodies two mathematical principles at once. It is rigid in angle, yet flexible in extension. The number 6 is non-negotiable. The length of each arm is not. The necessity of hexagonal symmetry also explains why 5-fold or 7-fold snowflakes do not occur naturally under normal atmospheric conditions. 5-fold symmetry appears in some molecular clusters and in certain biological forms, but it is incompatible with a repeating translational lattice in 3-dimensional space. A periodic crystal cannot fill space evenly with 5-fold rotational symmetry. 6-fold symmetry can. This is a quiet but firm boundary. Mathematics excludes certain possibilities long before observation confirms them. The snowflake, when seen through this lens, becomes less mysterious and more disciplined. Its symmetry is not fragile decoration. It is a declaration of internal order projected outward. Every arm grows from a lattice that repeats invisibly beneath it. Every 60-degree angle reflects a crystallographic axis determined long before branching begins. Even when later instability creates intricate patterns, the foundation remains unchanged. Symmetry in snow is not imposed from above. It rises from below, from repeating points in space, arranged with unwavering regularity. What appears delicate at the surface is supported by strict geometry underneath. In winter light, a snowflake may seem fleeting, but mathematically it is uncompromising. Symmetry explains why a snowflake has 6 arms. It does not explain why those arms branch the way they do. For that, mathematics must shift from structure to process. Once growth begins in a vapor-rich environment, the pattern that emerges is shaped by how particles arrive, attach, and compete for space. One of the most useful models for understanding this is called diffusion limited aggregation, often abbreviated as DLA. Diffusion limited aggregation describes a process in which particles move randomly through space and stick when they encounter a growing cluster. Over time, this simple rule produces branching, tree-like forms. The pattern looks organic, yet it arises from repetition of a minimal instruction: wander, touch, attach. In a cloud, water vapor molecules drift in similar fashion. Their motion is influenced by random collisions with air molecules. When they reach the surface of a crystal, they may bind. Because the outermost tips of a crystal extend further into vapor-rich space, they receive more incoming molecules. The tips grow faster and branching intensifies. DLA captures this principle without requiring complex chemistry. The resulting structures often exhibit what is known as fractal geometry. A fractal is a pattern that shows similar structure at different scales. Fractal dimension refers to a way of measuring how completely a pattern fills space, often resulting in a non-integer value between traditional dimensions. A dendritic snowflake arm does not behave like a simple line, nor like a solid plane. Its branching gives it a dimensional complexity somewhere in between. The mathematician Benoit Mandelbrot formalized fractal geometry in the 20th century, showing that coastlines, clouds, and plant structures share scaling properties. Snowflakes fit naturally into this framework. The main arm branches. Each branch subdivides. Sub-branches repeat the logic of the whole. The repetition is not exact, but it is statistically consistent. Nature rarely requires elaborate instructions to produce complexity. In many systems, intricate forms arise through what physicists call self-organized criticality. Self-organized criticality means that a system naturally evolves toward a threshold state where small events can trigger large structural changes. In snowflake growth, a minor fluctuation in vapor concentration can redirect branching dramatically. The system balances near instability. This leads to a tension between determinism and chaos. Determinism means that outcomes are governed by physical laws and initial conditions. Chaos means that small differences in those initial conditions can lead to vastly different results. Snowflake formation belongs to both categories. The laws are fixed. The outcomes vary. A slight variation in humidity or temperature at a single moment may alter an entire arm's architecture. Computer simulations have made this visible. By encoding growth rules into algorithms, researchers can generate artificial snow crystals on a screen. These growth simulation algorithms calculate diffusion rates, attachment probabilities, and directional biases. Starting from a simple hexagonal seed, virtual crystals expand outward, branching according to programmed physical constraints. Some models rely on cellular automata. A cellular automaton is a grid-based computational system in which each cell changes state according to rules applied to its neighbors. Stephen Wolfram demonstrated how simple rule sets can generate unexpected complexity. In snowflake modeling, each grid cell may represent ice or vapor. Depending on neighboring states and threshold values, cells transition, mimicking crystal growth. The patterns generated by these simulations often resemble natural dendrites with striking accuracy. The resemblance is not coincidence. When diffusion, anisotropy, and supersaturation are translated into computational rules, the same structural tendencies appear. Mathematics does not decorate snowflakes. It reconstructs them. Fractal branching in snow also parallels forms found elsewhere in nature. Fern leaves display repeating subdivisions along a central stem. River networks divide into tributaries. Lightning forks through the sky in branching arcs. These systems differ in material and energy source, yet they share diffusion-like growth under constraint. The similarity lies in process, not substance. Even frost patterns that spread across a window pane on a cold morning follow comparable rules. As water vapor freezes on glass, branching lines extend outward from nucleation points. The patterns are thinner and more surface-bound than airborne crystals, but the governing dynamics are related. Diffusion and instability collaborate again. When observed closely, a snowflake becomes less an ornament and more a record of iterative computation. Each new layer is the result of local conditions applied repeatedly. There is no central designer. There is only rule and response. Mathematical modeling does not reduce wonder. It refines it. By understanding diffusion limited aggregation, fractal dimension, threshold dynamics, and algorithmic simulation, the branching of a snowflake becomes readable. Not predictable in exact detail, but understandable in principle. The snowflake, suspended in cold air, is therefore both geometry and algorithm. It obeys fixed lattice symmetry, yet its surface complexity unfolds through dynamic modeling principles. Within its delicate arms lies a conversation between randomness and rule, resolved not by intention, but by mathematics operating patiently in the atmosphere. Not every snowflake becomes a star. Some remain simple. Some stretch into columns. Some flatten into thin plates so delicate they almost resemble glass filings. The diversity of snow crystal forms is not decorative excess. It is classification written by temperature and humidity. The simplest form is the hexagonal prism. This is the basic three-dimensional shape that forms immediately after nucleation and early growth. A simple hexagonal prism looks like a tiny, elongated six-sided column with flat ends. It reflects the internal hexagonal lattice without additional branching. In certain atmospheric layers, especially where supersaturation is modest and temperature conditions remain stable, crystals may remain close to this fundamental geometry. As temperature shifts slightly, the balance of growth changes. When lateral growth along the basal plane becomes dominant, thin plates begin to form. A plate crystal is flat and wide, extending outward along 6 directions. Under particular humidity conditions, these plates can develop internal sector patterns, forming what are known as sector plates. Sector plates show visible divisions within the hexagon, subtle wedge-shaped regions that hint at internal growth variations. At colder temperatures, particularly near -15 degrees Celsius, with sufficient moisture, stellar dendrites emerge. These are the classic snowflakes most people imagine. Stellar dendrites possess 6 primary arms radiating from a central point, and each arm branches repeatedly into secondary and tertiary structures. The term dendrite means tree-like. The resemblance to a branching tree is structural, not symbolic. Growth instability amplifies tiny protrusions, allowing arms to subdivide in increasingly intricate ways. In Canada, especially during moist winter storms, stellar dendrites have been recorded with remarkable clarity. Historical photographs from Vermont Jericho show crystals so elaborate that each arm appears individually sculpted. These images were captured by Wilson Bentley, who spent decades photographing snowflakes under a microscope. His work revealed that while symmetry is constant, detail varies endlessly. Columnar forms represent another major family. When vertical growth along the crystallographic C-axis becomes dominant, crystals elongate into columns. A solid column is compact and prism-like, extending upward and downward with minimal lateral spread. These forms are common at temperature ranges where basal growth is suppressed, but vertical growth is encouraged. In colder continental climates, such as parts of Siberia, needle crystals frequently appear. Needles are slender, elongated structures that can resemble tiny ice splinters. They form within a relatively narrow temperature window, typically around -5 degrees Celsius. Under these conditions, molecular attachment favors extension along the vertical axis. The result is a shape that looks minimal compared to dendrites, but is equally precise in origin. Temperature ranges guide these families. Around -2 degrees Celsius, thin plates are more common. Near -5 degrees Celsius, needles and columns dominate. Around -15 degrees Celsius, stellar dendrites flourish if humidity supports branching. Slight variations in supersaturation determine whether a plate remains smooth or develops sectors, whether a column thickens or narrows. The classification of snow crystals therefore reflects atmospheric layering. In regions influenced by lake effect snow, such as areas downwind of the Great Lakes, unique growth conditions arise. Lake effect snow occurs when cold air passes over relatively warmer water, picking up moisture before moving inland. The increased humidity promotes rapid crystal growth, often encouraging large dendritic structures. The size and intricacy of these flakes reflect the abundance of available vapor. Sector plates illustrate how even within one family, variation persists. A sector plate maintains overall hexagonal symmetry, but displays internal ridges that divide each face into distinct segments. These ridges form because certain growth directions temporarily outpace others. The crystal records shifts in humidity and temperature as subtle structural accents. Solid columns can transition subtly into hollow or capped forms under changing conditions, yet within their core identity, they remain part of the columnar family. Their faces remain flat and well-defined. Their edges are sharp. Their symmetry remains intact, even without branching. The restraint of a solid column is not simplicity. It is environmental discipline. Stellar dendrites, by contrast, reveal what happens when supersaturation rises and diffusion accelerates. Each arm extends outward, then branches when local instability amplifies small irregularities. The process is cumulative. Branching does not appear all at once. It unfolds gradually as the crystal travels through vapor-rich layers. Needle crystals in Siberia often form in dry, cold air masses where moisture is limited, but temperature aligns with vertical growth preference. These needles may fall densely, creating fine, powdery snowfall. Their narrow shape affects how they accumulate on the ground, influencing snowpack texture. Wilson Bentley's work in Vermont Jericho documented thousands of snow crystals, showing that no two were identical in detail. Yet his images also reveal consistency in family classification. Plates remain plates. Columns remain columns. Dendrites maintain six-fold symmetry, even when arms vary in length or branching. The diversity of snow crystals is therefore organized, not chaotic. Each family corresponds to a window of atmospheric conditions. Within that window, microvariations create detail. But the overarching form obeys thermodynamic boundaries. A snowflake does not choose to become a plate or a column. It becomes what its environment permits. Temperature defines the dominant growth axis. Humidity determines whether that axis extends smoothly or branches. Time within specific layers determines how long that growth continues. Seen this way, morphological classification is less about naming shapes and more about reading atmosphere. A plate suggests one range of conditions. A needle suggests another. A stellar dendrite suggests moisture and instability at a specific temperature band. The sky writes in geometry. And each falling crystal carries its own classification, shaped not by intention, but by the quiet physics of cold air. Not all snow crystals remain pristine as they fall. Many encounter changing environments that alter their surfaces, attach new material, or merge them with others. These transitional and composite forms reveal that snow is not a static geometry, but an evolving structure shaped by motion, collision, and moisture. One of the most common transformations is rimming. A rimed crystal forms when a snow crystal collides with supercooled water droplets, liquid droplets that remain unfrozen below 0 degrees Celsius. When these droplets strike the crystal, they freeze instantly upon contact. The process coats the delicate structure in opaque ice. Fine branches may become thickened, and sharp edges soften beneath layers of frozen droplets. If rimming continues intensely, the original crystal can become nearly unrecognizable. In highly humid storm systems, where supercooled droplets are abundant, heavy rimming produces graupel. Graupel consists of soft, rounded pellets formed when ice crystals accumulate thick coatings of frozen droplets. The result resembles small, white beads rather than structured flakes. Graupel falls faster than typical dendrites because its compact shape reduces air resistance. High-moisture winter storms frequently generate graupel. In such conditions, turbulence keeps crystals suspended within droplet-rich regions. Each collision adds mass. The original symmetry becomes buried beneath accumulated ice. What began as a six-armed structure becomes a rounded particle shaped more by collision than by lattice growth. Another transitional form appears when individual snow crystals collide and adhere to one another without losing their original shapes. These clusters are known as aggregates. Aggregation occurs when delicate arms interlock during descent. The crystals bind lightly, forming irregular, multi-crystal clusters. Aggregates are fragile. Their bonds are weak, yet they significantly increase the apparent size of falling snowflakes. Aggregation becomes more likely when air temperatures hover near freezing, allowing slight surface melting that enhances adhesion. Large, fluffy snowflakes, often seen in calm winter snowfall, are typically aggregates rather than single crystals. Their size reflects collective binding rather than individual growth. Some columnar crystals develop additional structural features when they pass through varying atmospheric layers. A capped column forms when a column-shaped crystal enters a region that favors plate growth. Thin, plate-like structures develop on one or both ends of the column. The result resembles a central rod with flat caps attached. This composite structure records multiple growth environments within a single descent. Bullock rosettes represent another complex form. These structures consist of multiple elongated columns, or bullets, radiating outward from a central point. They often form in extremely cold conditions, particularly in high altitude or polar clouds. In Arctic regions, Bullock rosettes have been observed in cirrus layers, where temperatures are far below -20 degrees Celsius. Their geometry is angular and clustered, resembling crystalline spokes. Surface roughening is a more subtle transformation. Under rapid growth conditions, crystal faces may lose their smooth, faceted appearance. Instead of remaining flat and sharply defined, surfaces develop microscopic irregularities. Surface roughening reflects instability at the molecular scale, where growth rates fluctuate faster than the lattice can maintain smoothness. Jet stream dynamics can influence such transformations. Strong upper-level winds transport crystals across large horizontal distances, moving them through varying temperature and humidity fields. As a crystal travels within jet stream flow, its growth environment shifts rapidly. Caps may form. Rimming may begin or stop. Surface textures may change. The final structure becomes a layered record of atmospheric passage. In the Arctic, Bullock rosettes and capped columns are frequently documented in ice cloud observations. These forms contribute to radiative properties of high-altitude clouds, affecting how sunlight and infrared radiation interact with the atmosphere. Their geometry influences scattering behavior, linking microscopic shape to planetary energy balance. Institutions such as the National Snow and Ice Data Center collect data on snow crystal types and their influence on climate systems. Morphological diversity is not merely aesthetic. Different crystal shapes affect snowfall density, reflectivity, and accumulation patterns. Shape alters how snowpack forms and how light interacts with the surface. Meteorological organizations, including NOAA, monitor winter storm structures where graupel, aggregates, and rimed crystals dominate. The presence of graupel can signal strong updrafts within a storm system. Aggregates may indicate calmer descent and near-surface moisture. Morphology becomes a diagnostic tool. In transitional and composite forms, the snow crystal reveals its vulnerability to circumstance. A pristine dendrite may become rimed and rounded. A slender column may grow plates at its ends. Several crystals may bind into a single drifting cluster. The environment does not erase structure. It modifies it. These hybrid shapes remind us that classification is not rigid. Between the clean geometry of basic families and the rounded pellets of graupel lies a continuum of interaction. Snow in motion accumulates experience. Each collision, each layer crossed, each droplet encountered contributes to its evolving form. By the time such crystals reach the ground, they carry within them the memory of turbulence, humidity, altitude, and airflow. Transitional forms are not deviations from order. They are extensions of it, shaped by encounter rather than isolation. Once a snowflake completes its growth within a cloud layer, it does not immediately reach the ground. Between formation and landing lies a quiet descent shaped by gravity, air resistance, turbulence, and subtle physical exchanges. Falling is not passive. It is another stage of transformation. The first concept governing descent is terminal velocity. Terminal velocity is the constant speed an object reaches when the force of gravity pulling it downward is balanced by air resistance pushing upward. For snowflakes, this speed is remarkably slow. Large stellar dendrites, with their wide branching arms, can counter significant drag. Their broad surfaces catch air like miniature parachutes. As a result, they may fall at only 1 meter per second or less. Smaller, compact crystals fall faster. A rimed pellet or dense graupel particle encounters less air resistance relative to its mass. Shape determines speed. Speed influences how long a crystal remains within particular atmospheric layers. The longer it falls through moist air, the more opportunities it has for interaction. Descent is rarely straight. As air flows unevenly around a snowflake, it can begin to rotate. Aerodynamic rotation occurs when slight asymmetries in shape or airflow create torque, causing the crystal to spin. This rotation is usually gentle, sometimes irregular. For broad dendrites, rotation can slow descent further by increasing effective drag. Large dendritic flakes often drift rather than drop. Their descent may appear hesitant, almost suspended. In calm conditions, they move in subtle arcs, influenced by minor air currents invisible to the eye. This slow fall increases the likelihood of interaction with other particles. When two snow crystals approach one another, their probability of sticking together depends on collision efficiency. Collision efficiency refers to the likelihood that two particles will not only collide, but remain attached. Airflow patterns can cause particles to deflect around one another rather than meet directly. For attachment to occur, physical contact must align in a way that allows bonding. Aggregation mechanics describe how crystals bind once contact occurs. Delicate arms may interlock. Slight surface melting near temperatures close to freezing can create a thin liquid layer, enhancing adhesion. Aggregation is more common in humid, relatively warm winter air. It is less likely in very cold, dry conditions where surfaces remain rigid and brittle. Electrical charge can also influence interactions. Snow crystals often carry slight electric charges generated by frictional contact with air molecules or collisions within clouds. Charge interaction means that opposite charges attract while like charges repel. Although these charges are small, they can subtly increase the probability of adhesion during collisions. Studies of atmospheric electricity show that even weak charge differences can alter aggregation rates. In regions of turbulent winter storms, charge separation becomes more pronounced. Crystals may cluster more readily under certain electrostatic conditions. The influence is modest, but measurable. Sublimation represents a quieter transformation. Sublimation is the direct transition from solid ice to water vapor without passing through a liquid phase. When a snowflake falls into dry air, especially below cloud base, sublimation can gradually reduce its size. The crystal loses mass molecule by molecule, becoming thinner or even disappearing entirely before reaching the ground. Dry air sublimation is common in arid or cold continental climates. A snowflake may form high above, begin its descent intact, and fade invisibly into vapor before arrival. This phenomenon contributes to what meteorologists call virga, precipitation that evaporates before touching the surface. Airflow patterns during descent were central to early dynamic meteorology. Wilhelm Bjerkens advanced the understanding of atmospheric motion by applying fluid dynamics to weather systems. His work laid foundations for explaining how air currents influence precipitation paths. Snowflakes are subject to the same principles governing large-scale air movement. Within turbulent air, crystals may experience upward drafts strong enough to delay descent. In certain storm systems, repeated lifting cycles allow crystals to pass multiple times through moisture-rich layers. Each pass increases opportunities for growth, rimming, or aggregation. Descent becomes a looping trajectory rather than a single fall. Large dendrites descending slowly may collide with smaller crystals, rising in gentle updrafts. These interactions create aggregates of varied structure. Compact forms fall faster, moving quickly through layers and encountering fewer collisions. The interplay between speed and environment determines final morphology. Rotation affects how surfaces encounter airflow. A spinning crystal presents different faces to incoming air, altering local vapor gradients. Even during descent, slight growth or sublimation can continue, though more slowly than within dense cloud layers. The snowflake remains responsive until the very end. Electric charge effects are often subtle enough to escape casual observation, yet laboratory studies confirm their presence. Collisions in clouds can produce charge separation, and these charges influence microphysical processes. Snowfall is therefore not only mechanical, but also electrostatic. Terminal velocity is not fixed. As a snowflake gains mass through aggregation or rimming, its speed increases. As sublimation reduces mass, speed decreases slightly. The descent is dynamic, recalculated continuously by changing mass and drag. By the time a snowflake approaches the surface, it has passed through shifting temperatures, varying humidity, intermittent turbulence, and potential electrical fields. Its descent is a record of balance between gravity and air, between attachment and loss. Falling snow may appear serene from the ground, but within each drifting crystal lies a quiet negotiation. Speed adjusted by shape, rotation influenced by asymmetry, collisions guided by airflow and charge, molecules departing silently through sublimation. The sky does not simply release snow. It escorts it downward through layers of physics, each one refining the crystal until it meets the earth or dissolves back into air. When a snowflake reaches the ground, its individuality does not end. It changes role. What was once a drifting crystal becomes part of a collective structure known as snowpack. Snowpack is simply the accumulated layers of snow resting on the surface. But within that quiet accumulation, transformation begins almost immediately. Snow on the ground is not static. Even at low temperatures, ice molecules continue to move slightly within the solid. Over time, sharp edges soften, delicate branches collapse, and contact points between neighboring crystals strengthen. This gradual internal restructuring is called snowpack metamorphism. Metamorphism here means change in form without melting into liquid water. One of the primary processes within snowpack is sintering. Sintering refers to the bonding of adjacent ice grains through molecular diffusion. When two crystals touch, molecules migrate across their boundary, thickening the connection. The contact area grows and the bond strengthens. Individual flakes lose their distinct outlines as they fuse into a more cohesive mass. As sintering progresses, the original intricate geometry of dendrites disappears. What remains are rounded grains connected by solid bridges. Snow becomes denser. Air pockets shrink. The texture shifts from soft and powdery to compact and supportive. Temperature plays a critical role in determining how snowpack evolves. When temperatures remain relatively uniform throughout the snow layer, grains tend to become rounded and more stable. But when there is a strong temperature difference between the ground and the surface, a different process begins. Temperature gradient metamorphism occurs when warmer air near the ground and colder air above create a gradient through the snowpack. This gradient drives vapor movement upward. Water molecules sublimate from warmer grains and deposit onto colder ones higher in the layer. Over time, this creates angular, faceted crystals within the snowpack. These faceted crystals weaken structural cohesion. Instead of rounded grains tightly bonded, the snow develops larger, angular particles with weaker connections. This internal rearrangement can create fragile layers buried beneath newer snowfall. Such layers are often associated with avalanche risk. Avalanches are not simply surface slides. They often result from a weak layer collapsing under the weight of overlying snow. When temperature gradient metamorphism produces poorly bonded crystals, the snowpack becomes stratified. A dense slab resting above a fragile layer may fracture suddenly, releasing a cascade downslope. In colder polar regions, where snowfall accumulates year after year without fully melting, long-term transformation continues. Fresh snow gradually compacts under its own weight. Air spaces diminish, grains recrystallize, and become tightly packed. Over time, snow transitions into firn. Firn is intermediate material between snow and glacial ice. It forms through prolonged compaction and recrystallization, typically over several years. Firn retains some air, but is significantly denser than fresh snow. Continued compression eventually forces out remaining air, transforming firn into solid glacial ice. The vast ice sheets of Antarctica are composed of layers that began as individual snowflakes. Over thousands of years, accumulated snowfall compacted into firn and then into dense ice hundreds to thousands of meters thick. Each layer preserves subtle chemical signatures of the atmosphere at the time it fell. Similarly, the Greenland ice sheet represents centuries of compressed snowfall. Ice cores extracted from Greenland reveal annual layers preserved within the frozen mass. These layers allow scientists to reconstruct past climates, volcanic events, and atmospheric composition. What began as fragile crystals becomes a climatic archive. Snow on the ground also influences energy exchange through albedo. Albedo refers to the reflectivity of a surface. Fresh snow has high albedo, meaning it reflects a large portion of incoming sunlight back into space. This reflection cools the surface and influences regional temperature patterns. As snow ages, becomes compacted, or accumulates impurities, albedo decreases slightly. The cryosphere encompasses all frozen water on Earth, including snowpack, glaciers, sea ice, and ice sheets. It plays a critical role in regulating global climate. Changes in snow cover affect how much solar radiation the planet absorbs. Reduced snow and ice lower albedo, increasing heat absorption and amplifying warming. Climate scientists such as James Hansen have emphasized the importance of polar ice in maintaining planetary balance. Loss of snow cover and ice mass alters global energy distribution. Monitoring these changes has become central to climate research. Programs such as the NASA Cryosphere program track snow and ice extent using satellites and field measurements. Data collected from polar regions and mountain snowpacks help scientists understand long-term trends in ice mass, seasonal variation, and feedback loops between surface reflectivity and atmospheric temperature. The journey of a snowflake, therefore, continues long after it lands. It bonds, reshapes, compresses, and eventually may become part of glacier or ice sheet. It may influence avalanche formation or reflect sunlight back into space. It may preserve a chemical trace of a distant volcanic eruption within polar ice. On the ground, snow becomes structure. Structure becomes archive. Archive becomes climate memory. The fall may be brief, but the impact can endure for centuries. In the quiet accumulation of winter, individual geometry dissolves into collective transformation. What drifted softly through cold air becomes part of the planet's frozen skin, shaping landscapes, storing history, and regulating light itself. Snowflakes have always arrived like a message written in a language that vanishes as soon as it is read. For most of human history, they were simply weather, a soft inconvenience, a quiet beauty, a sign of seasonal change. But at some point, someone looked closer and noticed something strangely consistent. Not snow is white, not snow is cold, but that many snowflakes carried a kind of order, a repeated geometry, a persistence of angles that seemed too steady to be accidental. In northern Europe, where winter is not an occasional visitor but a long companion, early descriptions of snow began to include its forms. Olaus Magnus, writing in the 16th century about life in the Nordic world, documented ice and winter phenomena with the attention of someone living inside them. His descriptions were not microscopic, because the tools did not yet exist, but they were observational in the truest sense. Snow was not treated as featureless powder. It had structure. It behaved in patterns. It hinted at design. Those early observations were limited by the human eye, and the human eye is both powerful and narrow. Snow crystals are small, and their finest details dissolve into glare unless they land on something dark. Even then, the time window is short. A flake melts. It sublimates. It fractures. It disappears. So early curiosity had to be fast, but also careful. The problem was not a lack of wonder. It was the speed of loss. The 17th century changed the situation because glass lenses began to change what counted as visible. Early microscopes were imperfect, but they opened an entirely new world. Things that had been guessed at could now be drawn. Surfaces, textures, repeating structures, the strange elegance of natural materials. Snowflakes, which had always seemed to vanish without leaving evidence, could now be examined in a way that approached study. This is where the role of drawing became crucial. Photography did not exist. Memory was unreliable. If you wanted to preserve a snow crystal, you had to translate it into lines. And those lines needed to be accurate enough to carry the geometry forward into a later moment, when the flake itself was gone. Robert Hooke entered this world with the seriousness of someone who believed that careful looking was a form of discovery. In Micrographia, he presented magnified drawings of many natural objects, and among them were snow crystals. Hooke did not treat them as ornament. His sketches tried to hold on to the proportions, the branching logic, the repeating angles. He captured something that feels modern in hindsight, the sense that nature repeats rules at small scales, and that those rules can be recorded. But recording snowflakes was not only a matter of observation, it was also a matter of technique. A snowflake could be examined briefly, but the final record often had to be etched or engraved into copperplate, because printing was the medium through which knowledge traveled. Engraving required decision. You had to choose which lines mattered, which curves were essential, which symmetry was real, and which was merely suggested by the eye. In that sense, the early visual history of snowflakes is also a history of interpretation. Still, some features were too consistent to ignore. Again and again, the same basic geometry appeared: six-fold symmetry, 6 arms, 6 directions, 6 angles repeating around a center. The details differed, but the scaffold remained. That repetition quietly pressured early thinkers into asking deeper questions. Johannes Kepler approached the puzzle in a way that now feels almost cinematic. A mathematician noticing winter. In 1611, he published Strena su de Nive Sexangula, a small treatise often translated as a New Year's gift of hexagonal snow. Kepler's central question was simple and unsettling. Why 6? Why not 5 or 7 or any other number? Why would nature keep returning to the same count? Kepler did not have molecular theory, but he had geometry, and he had a mind trained to respect patterns. He proposed that if snow was built from tiny, identical units, then the most efficient way those units could pack together might naturally produce hexagonal arrangements. His answer was not fully correct in the modern sense, But it was important for a different reason. It suggested that snowflake symmetry was not an aesthetic accident. It was a consequence. That shift mattered. Once you accept that snowflakes might follow rules, you begin to treat them differently. They stop being decorative weather and become evidence. The snowflake becomes a small laboratory falling from the sky, repeating the same experiment millions of times each winter. In early Europe, this idea lived alongside other explanations. Some thinkers saw symmetry as a sign of divine order. Others believed it was the product of hidden mechanical forces. But even the disagreements kept the snowflake alive as a topic, because everyone involved sensed that the repetition meant something. It was a visible clue to an invisible structure. What made the fascination durable was the combination of sameness and difference. Snowflakes seemed to share a central rule, yet their branching patterns never matched perfectly. That paradox forced a new kind of curiosity. How can a system be strict and unpredictable at the same time? How can it obey a rigid symmetry while producing endless variation? Even without modern terminology, early observers were already circling around the idea that simple constraints can generate complex outcomes. The early scientific story of snowflakes is not the story of one sudden discovery. It is the slow accumulation of attention. A few sketches, a few engravings, a few printed pages that carried the image of a snow crystal beyond the winter day it fell. Curiosity did not advance by speed, but by persistence. And perhaps that is why snowflakes became such an enduring scientific object. They rewarded careful looking, but they did not tolerate carelessness. They required patience, timing, and respect for detail. They invited the kind of mind that can hold a question gently for years, not trying to force an answer, but refusing to let the pattern be dismissed. By the end of that early period, the snowflake had already done something remarkable. It had convinced serious thinkers that the atmosphere could produce geometry, that cold air could write structure, that a fleeting object could contain a rule. And once a rule is suspected, science does not stop looking. The modern study of snowflakes begins where early curiosity left off, with better tools and sharper resolution. The central questions remain familiar. How does structure form? Why does shape vary? But the instruments have changed. Where early observers relied on glass lenses and engraving plates, modern science relies on vacuum chambers, satellite sensors, and computational models that track individual crystals across continents. One of the most transformative tools has been the electron microscope. An electron microscope uses a beam of electrons instead of visible light to produce images at extremely high magnification. Because electrons have much shorter wavelengths than light, they reveal details at the nanometer scale. In snow crystals, this means researchers can observe surface textures, growth steps, and molecular-level irregularities that were once invisible. Cryogenic scanning electron microscopy, often called cryosym, allows scientists to examine ice without melting it. In this method, a snow sample is rapidly frozen and maintained at very low temperatures inside a vacuum chamber. The electron beam scans the surface, producing high-resolution images. These images reveal micro-roughness, faceting patterns, and subtle surface transformations that occur during growth and sublimation. Modern laboratories no longer depend solely on waiting for natural snowfall. Controlled crystal growth can be reproduced indoors. In carefully regulated environments, scientists adjust temperature, humidity, and airflow to grow individual ice crystals on fine substrates. By modifying one parameter at a time, researchers isolate how specific atmospheric conditions influence morphology. Cloud chambers extend this control further. A cloud chamber is an enclosed space where temperature and vapor pressure can be manipulated to simulate atmospheric conditions. Modern cloud chamber experiments allow scientists to generate ice crystals within precisely defined environments. Researchers can replicate conditions corresponding to different altitudes. observing how slight variations in supersaturation alter branching behavior. High-speed camera analysis adds another dimension. By recording crystal growth in real-time at microscopic scale, researchers can observe branching instabilities as they unfold. High-speed imaging captures the moment when a flat surface begins to roughen or when a protrusion accelerates into a branch. Growth is no longer inferred solely from final structure. It is observed as a process. These experimental insights feed directly into climate science. Snow crystal shape affects how light interacts with clouds and snowpack. Radiative transfer, the movement of energy through the atmosphere, depends on particle geometry. Flat plates scatter light differently than columns. Aggregates reflect differently than graupel. To model Earth's energy balance accurately, these variations must be quantified. In global climate models, snow crystal parameters represent simplified descriptions of particle shape, size distribution, and density. These parameters influence how clouds reflect sunlight and trap infrared radiation. Even minor adjustments in assumed crystal geometry can alter modeled temperature projections. What seems delicate at microscopic scale becomes significant at planetary scale. Satellite observations now complement laboratory work. Space-based instruments detect cloud properties by measuring reflected sunlight and emitted thermal radiation. By analyzing scattering patterns, scientists infer the presence of ice crystals and estimate their typical shapes. Satellites provide global coverage, linking localized microphysics to worldwide patterns. Organizations such as the World Meteorological Organization coordinate data sharing across nations. Snowfall measurements, cloud observations, and atmospheric modeling contribute to international datasets. Standardized reporting ensures that snow microphysics research informs weather prediction and climate monitoring consistently across regions. The Intergovernmental Panel on Climate Change, known as the IPCC, synthesizes research findings into comprehensive assessments of climate trends. Snow and ice processes appear throughout these reports, particularly in discussions of albedo feedback and polar amplification. Ice crystal behavior influences cloud reflectivity, which in turn affects surface temperature projections. Modern modeling also accounts for aerosol interactions. Laboratory studies show how different atmospheric particles act as ice nuclei, influencing crystal formation rates. These findings help refine climate models by linking pollution levels, volcanic emissions, and natural aerosols to precipitation patterns. Remote sensing technologies now detect snowfall intensity and crystal characteristics in near real time. Radar systems measure backscatter signatures, which vary depending on particle size and shape. These measurements improve short-term weather forecasts and long-term climatological datasets. Computer simulations integrate all these layers. Microphysical models describe individual crystal growth. Mesoscale models simulate storm systems. Global circulation models project large-scale climate dynamics. Each level depends on accurate representation of ice processes. A snowflake becomes both a data point and a parameter. Modern research continues to refine understanding of sublimation rates, aggregation thresholds, and rimming efficiency under different atmospheric compositions. As global temperatures shift, the altitude and duration of snow-forming conditions change. Observing how crystal morphology responds to these shifts provides early indicators of broader environmental transformation. What began as sketches on copper plates has evolved into coordinated international research. Electron microscopes reveal surface terraces invisible to the naked eye. Cloud chambers recreate winter at controlled pressure. Satellites monitor polar ice expanses daily. Climate reports integrate these findings into global projections. Yet the essential motivation remains unchanged. Snowflakes are studied not because they are rare, but because they are precise. Their geometry records temperature, humidity, airflow, and time. Modern science does not replace early curiosity. It extends it with instruments capable of seeing deeper and measuring longer. In laboratories, in orbit, and within computational models, the snowflake continues to inform. It is no longer just an object of wonder. It is a variable in equations that describe Earth's climate system. Its six-fold symmetry still holds, but its implications now stretch far beyond a winter sky. Snowflakes do not last long enough to belong to permanence, and perhaps that is why they have come to symbolize it so effectively. They appear, settle, dissolve. A geometry that feels deliberate arrives without warning and disappears without residue. Across cultures, this brief presence has made the snowflake more than weather. It has become a quiet emblem of transience. Impermanence is not always understood as loss. In many traditions, it is treated as a reminder of attention. A snowflake cannot be stored in the hand. It cannot be owned in its original form. Its beauty exists in timing. That fragility has given it symbolic weight, particularly in literary and aesthetic traditions that value the fleeting. In Japanese winter aesthetics, snow is rarely dramatic. It is described softly, often in relation to silence, emptiness, or stillness. The falling of snow alters sound as much as sight. It quiets footsteps. It reduces contrast. It simplifies the landscape. Within this tradition, snow becomes a medium of restraint rather than spectacle. Haiku poetry reflects this restraint. A snowflake may not be described in detail, yet it shapes the emotional field of the poem. Matsuo Basho, writing in the 17th century, often invoked seasonal imagery that included winter stillness. Snow in haiku does not dominate. It frames. A few syllables carry the sense of a world temporarily softened. The snowflake here is not an object to analyze. It is a moment to notice. The symbolic connection between snow and ephemerality also appears in Western traditions, though often with different emphasis. In the Victorian era, winter imagery grew increasingly decorative. Snowflakes began to appear in printed cards, book illustrations, and holiday motifs. The crystal form, with its radial symmetry, lent itself easily to repetition in ornamental design. Victorian snow iconography often emphasized delicacy and purity. The six-armed structure became stylized, simplified into symmetrical motifs suitable for engraving and textile patterns. The snowflake transformed meteorological phenomenon into visual shorthand for winter itself. This stylization influenced Christmas decorations. Paper cutouts, glass ornaments, and later plastic and metal designs adopted the hexagonal symmetry of snow crystals. The branching arms were exaggerated for visibility and aesthetic balance. In many cases, the scientific accuracy of the crystal was secondary to its visual harmony. Yet the six-fold structure remained intact. Even in abstraction, the geometry persisted. Minimalist design later rediscovered the hexagon in a different context. The hexagon is structurally efficient. It tessellates without gaps. It conveys balance without rigidity. In modern graphic design, hexagonal grids appear in logos architectural motifs and layout systems. Though not always directly referencing snow, the cultural familiarity of six-fold symmetry carries subtle associations with natural order. The snowflake's geometry offers designers a rare combination: complexity that can be simplified without losing identity. Remove the intricate branching, and a six-pointed form still reads as snow. Reduce it further to intersecting lines at 60-degree intervals, and recognition remains. The structure is resilient to abstraction. Art Nouveau, emerging in the late 19th and early 20th centuries, embraced organic forms and flowing lines. Artists such as Alphonse Mucha incorporated botanical and natural motifs into decorative compositions. While snowflakes were not always central subjects, the movement's fascination with symmetry, repetition, and curvature resonates with crystalline patterns. Branching forms echo the same structural rhythm seen in dendritic growth. Snow as a symbol of purity and transformation also appears in visual storytelling. A landscape covered in snow suggests reset, concealment, or pause. The snowflake, multiplied into snowfall, becomes a veil. It simplifies color and softens edges. In art, this effect is often used to indicate emotional transition or reflective space. In Japanese aesthetics, winter scenes are frequently composed with restraint. Snow resting on rooftops or tree branches emphasizes negative space. The white surface does not overwhelm. It invites contemplation. The snowflake, though rarely depicted individually in traditional Japanese art, contributes to this collective visual quiet. The Victorian fascination with categorizing and collecting also influenced how snow was represented. Albums of snowflake illustrations circulated among enthusiasts. Though these were often based on observation, they leaned toward idealization. The snowflake became a token of refined natural beauty, suitable for parlor display. As printing technologies advanced, repeating snowflake motifs became easier to reproduce. Textile patterns incorporated radial symmetry. Wallpaper designs used geometric repetition inspired by crystalline forms. The snowflake entered domestic space not as cold, but as ornament. Symbolically, snow also came to represent silence. Sound behaves differently in snowy environments, absorbed and dampened by accumulated layers. This acoustic quality reinforced cultural associations between snow and calm. A single flake does not make silence, but it participates in it. The snowflake carries meaning far beyond weather. In haiku shaped by poets like Matsuo Basho, snow suggests quiet impermanence rather than spectacle. In Victorian ornament and Christmas decoration, its six-fold symmetry became a seasonal emblem, simplified yet instantly recognizable. Minimalist design later embraced the hexagon for its balance and structural clarity, while artists such as Alphonse Mucha echoed natural symmetry in flowing decorative forms. What endures culturally is the tension between order and disappearance, a precise geometry that exists only briefly, reminding us that beauty often arrives softly and does not stay. In the digital age, the snowflake no longer depends on winter to exist. It appears on screens long before it appears in the sky. A small icon in a weather app, a symbol in a temperature setting, a minimalist glyph indicating freeze. Digital icon design favors clarity and immediate recognition, and the snowflake's six-fold symmetry translates effortlessly into vector form. Even when reduced to a few intersecting lines, its identity remains intact. User interface systems rely on symbols that communicate instantly. Symmetry signals balance and stability, and the radial order of a snowflake centers attention without effort. In UI design, the snowflake becomes functional language. It no longer represents a specific crystal, but the concept of cold itself. Geometry becomes shorthand. In many digital environments, the snowflake is simplified to its structural essence. 6 spokes radiating at 60-degree intervals. Detail is removed, but proportion is preserved. The icon must scale from large displays to tiny notifications. The fact that it survives this compression speaks to the resilience of its geometry. Fractal art has taken snowflake logic into more complex territory. Using recursive equations, artists generate branching structures that echo natural dendrites. A fractal is a pattern that repeats at multiple scales, and snow crystals lend themselves naturally to this repetition. Digital tools allow branching to extend far beyond what atmospheric time would permit. Unlike physical snow, digital fractals do not melt. They can deepen indefinitely, each subdivision producing finer detail. Yet even in infinite recursion, the underlying symmetry remains stable. The mathematics holds the structure together, no matter how intricate it becomes. Three-dimensional simulation has added another layer to representation. Software now models crystal growth in virtual space, allowing researchers and designers to rotate, zoom, and illuminate structures from every angle. These 3D renderings reveal surface ridges and internal symmetry with a clarity impossible during natural snowfall. Such simulations are not merely aesthetic. They assist in understanding how branching instability unfolds, how faceting sharpens edges, how subtle environmental shifts alter morphology. The digital model becomes both visual and analytical tool. Observation extends beyond the limits of weather. Scientific data has also entered the aesthetic domain. Snowfall measurements, satellite observations of ice sheets, and atmospheric datasets are transformed into visual installations. Lines of data become branching light patterns. Temperature gradients become shifting color fields. The snowflake becomes a bridge between science and perception. In science museums, interactive displays invite visitors to adjust temperature and humidity controls to generate digital snow crystals. Each setting produces a new form, demonstrating how slight changes in conditions alter growth. The visitor sees cause and effect translated into geometry. Physics becomes participatory. Generative art projects embrace similar logic. Algorithms produce endless variations of crystalline forms, each distinct yet governed by shared rules. The snowflake becomes a framework for exploring randomness within constraint. Code replaces cloud, but structure persists. Artists working with large-scale data visualization, such as Refik Anadol, have explored immersive environments where information becomes architecture. Though not limited to snow, the principle is similar: invisible systems rendered visible through light and motion. Crystalline order translates naturally into spatial experience. Climate visualization graphics now incorporate snow and ice parameters into public communication. Charts representing ice mass loss, albedo change, or snowfall variability often echo branching or layered structures. Data is shaped to be readable, but also emotionally resonant. The snowflake becomes metaphor and metric at once. In digital animation, snow is simulated through particle systems that model descent, collision, and accumulation. Even here, the six-fold symmetry occasionally appears in close-up renders. The physical principles once studied under microscopes now guide computer graphics engines. Augmented and virtual reality systems have also begun to reinterpret crystalline geometry. In immersive environments, users can step inside magnified snow structures, walking between branching arms scaled to architectural size. What would normally dissolve on a glove becomes spatial experience. The crystal is no longer held in the hand, but inhabited. Educational platforms increasingly use interactive simulations to teach atmospheric physics through visual snow models. By adjusting virtual wind speed, vapor density, or temperature layers, learners watch structures morph in real time. The snowflake becomes a dynamic diagram, responsive rather than static, turning abstraction into movement. Even in motion graphics and cinematic design, crystalline transitions are used to signify freezing, memory, or pause. Branching lines radiate across a screen to indicate digital frost. The aesthetic is familiar enough to communicate instantly, yet flexible enough to evolve. The snowflake has become a visual verb as much as a noun. Across all these representations, the snowflake shifts from object to interface. It signals temperature, encodes data, structures art, and shapes virtual space. It no longer requires cold air. It exists as geometry alone. Each version feels briefly luminous, like a projection that fades as the screen refreshes. A rendered crystal dissolves into pixels. A generative pattern gives way to another. A data visualization updates and the form rearranges. An interactive model resets, and the branches grow differently the next time. A museum screen dims, and the crystalline lattice disappears into black glass. A climate graphic shifts scale, and the symmetry becomes statistics. Like a sculpture of frost that vanishes without leaving water behind, the snowflake persists not through permanence, but through pattern. It has moved from falling crystal to observed specimen, from engraved study to scientific model, from winter field to climate record. Yet its quiet law remains unchanged. Balance around a center, repetition at 60 degrees, structure unfolding outward with patient consistency. What once drifted briefly through cold air now endures as understanding, as symbol, as measured form. The material may melt, the season may pass, but the geometry continues, precise and restrained, dissolving and reappearing wherever order meets cold.